So here are the notes for section 3.2, which is with exponential logistic modeling, so word problems. So here's our exponential population model. So the population at any time t is given by p0, so your starting population whenever t is 0. This doesn't necessarily have to be year 0. So if you're starting from 1900, that year is 0. 1 plus r, where r is the rate of growth, or if it's losing population, r would be negative, and t is time in years. So if r is greater than 0, then p of t is an exponential. That should be the word growth in there. It's an exponential growth function, and its growth factor is the base of the exponential function 1 plus r. So if you grow at 5%, your growth factor is 1.05. If r is less than 0, the base 1 plus r is less than 1, and you have a decay function, and 1 plus r is the decay factor. So if you're losing 20% of your population, 0.8 is your decay factor. So example 1, tell whether the population model is an exponential growth function or exponential decay function. So here, that number is more than 1, so this is growth. The percent rate of change, you would take your given value, subtract 1 from it, and then multiply that by 100. So San Jose here is growing at 0.64% per year. Detroit, that number is less than 1, so the population is going down. 0.9858 minus 1 is, I'm lazy, get the calculator, 0.9858 minus 1. So this is negative 0.0142 multiplied by 100, so 1.42%. So Detroit's losing people at a rate of almost 2%. Okay, 2, determine the exponential function with initial value 12, so that's what goes outside, increasing at a rate of 8%, so 1 plus 8% as a decimal, raised to the t, so this becomes 12 times 1.08 to the t power. And that's your equation. All right, so example 3, so it's just word problem-y stuff. So suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 35. Okay, so we're trying to figure out this equation. So I start with 100. If it's doubling, this is going to be 2, and I'm going to put an n here because I don't want to put t, because I'm actually counting how many, in this case, n and t are actually going to be the same thing if you count in hours, but I'm just counting the number of doubles. And then at the end, I'm going to convert that back into the actual number. So I can do this step algebraically, so that's going to cancel 2 of my zeros out. So 3,500 equals 2 to the nth. And then I'm just kind of guessing. So let's try 100. That's way too big. Let's try 50. That's still way too big. Let's try 25. Still too big. Let's try 10. Too small. 2 to the 10th is 10, so 2 to the 12th. Too big. So 2 to the 11th. Too small. So 2 to the 11 and a half. Better. 2 to the 11.6. Better. 2 to the 11.7. Better. 11.8, too much. So 2 to the 11.71, 2 to the 11.72. And then you're just repeating this process over and over again until you get the number you want. 0.74, 2 to the 11.75. I'm not going to go any farther than this place. This one's probably going to be it. Nope, that's good. Let's see if we can get 7.8. Oh, too much. Okay, so we'll say n is 11.77. N is the number of doubles. It doubles every hour. So the time is about 11.77 hours. All right, so example 4, suppose the half-life of a certain radioactive substance is 20 days and its mass is 5 grams initially. So I have 1 equals, I want to end up at 1. I start with 5, I'm doing a half each time, and I'm going to count the number of half-lives. So once again, n is just a number, it's not going to be a time. So I can divide by the 5, so that works. So 1/5 equals 1/2 to the nth. So we'll make this 0.2 to make our calculations a little bit easier. We'll make this 0.5. Works the same way. So then we're doing our guess and check-in. So 0.5 to the second power. That's not quite big enough. So 0.5, or that's still too big, sorry, to the third. So we overshot it. So 0.5 to the 2.5. Nope. 0.5 to the 2. So we took too much off, so we need to count our exponent down because we need less time to go by. Now that looks pretty good. So n is 2.3. Oops. So that's the number I use for my variable. Now n counts the number of half-lives, and the half-life is 20 days. So 20 times 2.3 is 46 days. So remember, the way the half-life works is you lose half of it. So I started with 5. So after 20 days, I have half of what I started with. After another 20 days, I have half of that, which is now 1 1/4. So there's my 40 days. But if I go another half-life, if I go another full half-life, half of 1 1/4 is 0.625. So that's too far down. So I knew it had to be more than 40, but less than 60. So, okay. Scientists have established atmospheric pressure at sea level is 14.7 pounds per square inch. And the pressure reduced by half, so I'm going to do half-life again, for each 3.6 miles above sea level. This rule holds up to 50 miles above sea level. Find the altitude where pressure is 4 equals, I start at 14.7, it goes down by half, and once again I'm counting the number of halves, and then at the end I'm going to multiply by 3.6. So I can divide the 14.7 across. 4 divided by 14.7 gives me 0.272. I'll make this 0.5 to make our math easier. So here we go. So 0.5 raised. We'll start actually here at 2. We'll start at 2. So if I do 2, I get 0.25. So that might be too much. Let's try backing off a little bit. 1.9. So 1.8 is too much. So somewhere between 1.8 and 1.9. 0.85. No, the wrong way. 0.5 to the 1.86. 0.5 to the 1.87. 0.5 to the 1.88. That's probably the best we're going to get. So n is 1.88, but each n is 3.6, so 1.88 times 3.6 gives me about 6.7 miles above sea level. Will I finally be at 4 pounds per square inch? All right, so logistic models. So last example here. Watauga High School has 1,200 students. Bob, Carol, Ted, and Alice start a rumor which spreads logistically so that the number of students is equal to 1,200, given by this formula. Models the number of students who have heard the rumor by the end of day t. How many students have heard the rumor by the end of day 0? So here's my equation. So S of 0 is equal to 1,200. 1 plus 39. I'm going to be lazy. That's just going to be e to the 0th because negative 0.9 times 0 is 0. So this is the same thing as 1,200 over 1 plus 39, which is 1,200 over 40. So 120 divided by 40. So at the end of day 0, 30 students have heard the rumor. How long does it take for 1,000 students? Okay, so 1,000 equals 1,200, 1 plus 39 e to the negative 0.9 t. Now I'm going to kind of cross products this problem. Do a little bit of math here in my head. So this is going to move up, and I'm multiplying the diagonal, and that's going to move out here. So 1200 equals 1000 times 1 plus 39e to the negative 0.9t. So I have that equation. So algebraically, to solve this, I'm going to not write every step down. I need to divide my 1000 across. So now that guy's gone. Then I would need to subtract the 1 across. So now that guy's gone. Then I would need to divide by the 39. So that gives me, 0.00513 equals e to the negative 0.9t. And then from there it is guessing and checking. I will save you all some time and just tell you what the answer is, not make me watch it. So the actual answer is about 5.9 days for 1,000 students to hear the rumors, which brings us to the end of the section.